Hello guys, welcome back to TechDose, and in this video we will look at count submatrices with all ones problem, which is from Leetcode number 1504. There are a lot of problems which are similar to this. If you have already solved the largest rectangle in histogram, which is from Leetcode number 84, or maximal rectangle problem 85, which is based on this number 84 problem, then you will be able to relate the solution for this problem as well. Now this problem is based on the monotonic stack, which is used in the stock span problem as well as in the largest rectangle in histogram problem. So I have made detailed videos on all of these three. You can find all these solution links in the description below. Let's now look at the problem statement. In this problem, given an m by n binary matrix mat, return the number of submatrices that have all ones. A binary matrix means the values can either be 0 or 1 only. Now if you look at the first given matrix here, then we are required to count the number of submatrices that have all ones. So is this a valid submatrix? Yes. So the count is 1. Is this a valid submatrix? No, because you have a 0 here. Is this a valid submatrix? Yes. You can say you can add +1 count to it. Now this is also valid. This is valid. This is valid. Okay, so you can keep on counting all the valid submatrices and the count will be equals to 13. So that is why 13 is the answer. Now a simple approach in this case is to just start at a point I comma j. You can say that I am going for row number I and column number j, and try to expand, try to find out how many cells can you cover to the right and how many down cells can you cover. Depending on that, you can easily count the number of submatrices. So let's say that you have 1 1 1 0 and you had 1 1 0 1, and you were trying to count how many submatrices start at this given index I comma j. So I is the row number, j is the column number. Then you can start this count here because this is 1, so you can start the counter with 1. And if you can cover one more cell to the right, you can add +1. If you can cover one more cell to the right, you can add +1. Now since you have a 0 here, so you should not go to the right hand side, because even if you have a 1 here, this one cannot be a valid submatrix, right? So as soon as you see a 0 in the row, you will stop, and similarly in the column as well, you cannot go beyond this point. Okay, now go to the next row and try to find that you have another 1. So you add +1 to the count, because this will be a valid submatrix. You have another 1, so you add +1 to the count. And now you are seeing a 0, so you should not move forward. Okay, so this should be slicing, because if you go to the next row, and you have a 1 1 1, then you must only cover these two ones. You cannot cover this one because you have already seen a 0 here, right? Well, if you do it in this approach, then I comma j is considered as the top left corner of your submatrix. All these submatrices, whatever you are generating, is starting at I comma j, and we are adding +1 to the count only when we see a 1, right? So if you happen to follow this approach, then we will be considering each of the cell as the top left corner. And how many cells are there? M into n cells, where m is the number of rows, n is the number of columns. And you have to traverse through the entire matrix in the worst case, and the entire matrix size is also m into n, right? So you will have a multiplication factor with m into n. So this approach is m square n square, and this is your brute force approach. Okay, so if you follow the brute force approach, then you can easily count for all the starting point. Like for this starting point, how many valid submatrices will be present? 1 2 and 3 valid submatrices for 0 comma 0. How many submatrices are there at 0 comma 2? One submatrix only. How many at this as this 1 comma 0 as the top left corner? 1 2 3 and 4. So 4 submatrices, right? So similarly you can keep on counting here. 1 2, so 2 submatrices at this point as the top left corner. This will have 1 2, so 2 submatrices at this point, and this will only have 1. You can see if this is the top left corner, then this is only 1. So the count is 3 + 1 4 + 4 8 + 2 10 + 2 12 + 1 13. So that is how 13 is the answer, right? So I hope the brute force approach is clear. and you can try the brute force approach. I think it might pass, but if you do the calculation for m square n square, it will exceed your 10 to the power 8 number of computation. So if you have a more strict test case, then it should not pass, right? So we need something better than m square n square. If you write m square n algorithm or n square m algorithm, then this is going to pass. This is going to pass because if you calculate considering both m and n to be the max value of 150, it will come around 10 to the power of 6. You can just calculate it, okay? So I have to just target that my total computations are less than 10 to the power 8 to pass within 1 second, right? So we will be looking at the optimal solution anyway. So let's look at some idea. In this problem, let's consider our matrix to be 0, 1, 1, 0. Our goal is to count the submatrices with all the ones. In the brute force approach, I had showed that whenever you consider a coordinate I comma j, then I will be considering it as top left corner, right? While in the entire solution, I will be just considering I comma j as the bottom right corner, starting from this point onwards, okay? So let's consider this example, and if I have to count the number of valid submatrices, then I can just find out if this is the bottom right corner of the submatrix, then how many submatrices are possible? Well, 0 only, okay, because this is just a single row. If this is the bottom right corner, then 1 count. This is the only count. If this is the bottom right corner, then 2 count, because we have this 1 and this is 2. If this is the bottom right corner, then we have 3 count, 1, 2 and 3 count. And if this is the bottom right corner, well, this is already 0 and we cannot have 0, so this will give count 0. So what will be the total count? Here it will be 3 plus 2 plus 1, which is 6. So we will get 6 valid submatrices ending at any of these points as the bottom right corner. So the answer will be 6. But what if I extend this matrix and say that we had actually another row? Okay, 0, 1, 1, 0 was one row, and then the second row was 0, 1, 1, 0, 1. So how do you extend this problem? Let's say this problem was extended and it has 2 rows and it has 5 columns. Now in this case, what to do? Well, I will be calculating for each cell being the bottom right corner of the submatrix, and I have already calculated for first row, which is 6. Now let's calculate for the second row. When you start calculating for the second row, you will see that at this coordinate 1, 1, you have a 1. So how much can you extend to the left? You cannot extend to the left. It is 0. How much can you extend up? You can just extend by 1 height. So how many submatrices can you have? 1 and 2. So you will have a total count 2 here. For this, you can extend 1 time to the left, but not 2 times, because then you will see a 0. You can extend 1 time up. So the total count of submatrices ending at this point will be 4. And how I am saying 4? Because if you have 1, 1, 1, 1, the count of submatrices ending at this point, bottom right corner, will be 1, 2, then 3, and then 4. Okay, so this will always be equals to your gap multiplied by the height. Gap multiplied by height will always give you the number of submatrices ending at the bottom right corner of a cell. So the gap here is 2 and the height is 2. So 2 times 2 is 4, and that is how I got 4. For this 0, it will always be 0, because you cannot have a valid submatrix having 0. For this 1, you cannot extend anything to the left, you cannot extend anything up, so it will be 1. Total count here will be 0 plus 2 plus 4, which is 6, and 6 plus 1 is 7. So if you add this up, it will be 13. So 13 should be the total count for this particular matrix of size 2 by 5, whatever configuration I have given. So I hope you have got an idea of how the counting process happens for the valid submatrices, having considered that each of the point is the bottom right corner of a valid submatrix. If you know that, then you must have also understood that if I comma j is the bottom right corner, and if you have the gap 2 and height 3, then the total number of submatrices ending at this point ij will be gap multiplied by height, which is 3 times 2, it will be 6. 1, 2, then you have 3, and then you have 4, 5 and 6. It will always be equals to the gap multiplied by height, right? So in this example, the height is equals to 4, the gap is equals to 3. So the count of submatrices ending at this point will be equals to 12. 4 times 3. So I hope this formulation is clear. Now looking at the count of submatrices having 3, 3 as the bottom right corner in this particular example. What is 3, 3 by the way? If you see, this is 0, 1, 2, 3 and this is 0, 1, 2, 3. 3, 3 is this cell. If you try to consider this 3, 3 as the bottom right corner, then how many submatrices will be formed? Valid submatrices. Now if the height here is 2, then you cannot have a submatrix which has a height greater than 2. It is impossible, because if you consider a height greater than 2, let's say height 3, then this will contain at least one 0, because if it had no 0, then the height would not be 2, the height would be 3 already, right? So if I know that at this point the maximum run of ones in the height without seeing a 0 is 2, then I cannot have a rectangle ending at this bottom right corner, or a submatrix ending at this bottom right corner with a height more than 2. That means the rows more than 2. It is impossible. Okay. So I already know that the height will always be less than equals to 2 if I want to end a valid submatrix at this index 3, 3. Let's consider for height equals to 2. Okay. Now height equals to 1 can also be possible. When I say height less than equals to 2, height equals to 1 can also be possible, and this is also a valid submatrix, isn't it? But let's consider how to count for height equals to 2. To count for height equals to 2, we will create a slice, and this slice will keep on going until you see a 0. So this will be equals to your gap, and the gap is equals to 3 in this case. And what is the height? Height is equals to 2. So the number of submatrices which is ending at this 3, 3 as the bottom right corner will be equals to 6. The count equals to 6. But 6 is the count when I just consider height equals to 2. But height equals to 1 can also give the valid submatrix. Okay. So in that case, if I have to consider for all the heights less than this value 2, I have to see what is the first index on the left hand side where I have seen the height less than the current height, which is 2, because that will define what was the gap. How did we find the gap here equals to 3? The gap will be found by finding the previous smaller height. So if you have considered the height here, the first height will be 1, second will be 4, then you have 3, then you have 2. So if you find the previous smaller height, it will be this one. Okay, and this is at column number 0. So this 2 is at column number 3 and this is at 0. So you know the gap is 3 minus 0, which is 3. This is how you know the gap, and the height is 2 here. So 3 times 2 is 6. Now if you want to find out what are all the count of submatrices ending at this 3, 3 but has height less than 2, you consider this and find out how many submatrices are there which are ending at 3, 0 as the endpoint, because since its height is less than this height 2, you can always extend all the submatrices ending at this point and end it at 3, 3. The reasoning is, if you know that this is a submatrix, okay, and this is your coordinate I, j, and you know the count has come out to be gap multiplied by height, which is 9. But if you have some matrix on the left side, let's say it is a 2 by 2 size matrix and this is A, then if you know that at this A the count of submatrices ending at this A are 4, which is this 1, 2, 3 and 4, then you can extend all of these submatrices to end at this point B. How you can do that? If you consider this A, you can just extend it and end it at B. That is possible. If you consider this submatrix ending at A, you could have just extended it beyond this A and ended at B. Okay. If you consider this submatrix, then you could have just extended it and ended at B. Right? So the point is, when we see an A which has a height smaller than the height at B, then all the submatrices ending at A can be extended to end at B, and therefore the submatrices ending at B will be equals to this gap multiplied by this height plus the count of submatrices ending at this A, right? So that we will be considering to solve this problem. Now in this particular case, if I just want to count the number of submatrices ending at B as the bottom right corner with height equals to whatever is the height here at B, that means for this one it was 2, then it will just be equals to the gap multiplied by the histogram height at 3, right? Now why is this concept of histogram coming in? Whenever we solve this problem, you know that we will be solving it row wise, one row after another. So if you start solving it row wise, in this particular case, you will have the first row as 0, 1, 0, 0. So if you draw the histogram, it will be something like this, 0, 1, 0, 0. Okay. Now in this case, there is only one submatrix. Now if you go to the next row, then this row will be falling over the second row. And since the second row is 0, 1, 1, 0, you can just imagine it like a Tetris block, where if it falls on top of this ones, then the total sum is going to be you can say 0, 2, 1, 0. So if you draw the histogram for this, it will be 0, 2, 1, 0, 0, 2, 1, 0. Okay, now in this case, you have to count the submatrices ending at each of the cell. And similarly, when you go to the next row, row number 2, then you can imagine another row added, and you can imagine it like a Tetris block. You make one fall over the other, and so you will get the total sum as 0, 3, 2, 1. And now you find out the count of submatrices ending at each of the cell when you just consider this row. So these will be the height values. So the height values I will be maintaining in the histogram. So whenever I go from one row to the other, I will be adding the values. Now let's say that you had a 1 here, you had a 1 here, and you have a 0 here. Then in that case, when you add up, then since this is 0, this sum will remain to be 0, because as soon as you see a 0, 0 cannot be the base. The base must always be 1. You should always have continuous run of ones. That you must consider. This same concept we have also applied in the maximal rectangle problem. So I have already explained this 85. You must go through it. Maximal rectangle, where I have explained the exact same concept which is related to your 84 number problem. Okay. So this problem is also related to 84 and 85 with the same reasoning. So I hope you have understood why we are trying to maintain the previous smaller element, because I want to find out this A, so that I can simply multiply gap with height to count the number of submatrices ending at B, and also I will add the count of submatrices ending at this A and add them up. Okay, that's why we are maintaining the previous smaller element index. And the second thing, why this is a histogram problem, because we are solving it left to right, top down, and as we keep on solving, then all the previous items that you have seen on the top are actually considered. Okay, because each of the cell we are considering as the bottom right corner of a submatrix, right? Hence this works. So having known all this, you know that we will be applying the concept of previous smaller element plus the previous count, and you know that all the submatrices ending at ij here will be equals to this gap. That means, what is the height here? Height is 3. What is the height to the previous index? It is 4. And the previous to previous index, it is 2. So the previous smaller element of this 3 is at 2, which is at index 1, and this is index 3, so the gap is 2. So the gap is 2, the height is 3. So you multiply, and this will be equals to 3 times 2, which will be 6. But 6 is not the total count, okay? 6 is the count that you get from this region only. But if you look at this region, the count for the valid submatrices ending at P comma Q will be 4. Okay, which is by this height 2 and this gap 2. So this 4 needs to be added here as well, because these all can be extended to end at I comma j, which I have already explained. So that is why we will be considering gap times height plus the submatrices ending at p comma q as well, and that will be equals to 3 times 2 plus 4, which is 10, right? So I hope all the concepts are clear, and you know that to solve previous smaller element we have to take a monotonic stack, and that is why we will be taking monotonic stack which maintains increasing ordering. So each of the stack node will have 3 items, which is the height that we are seeing at the index, and whatever was the previous count of valid submatrices ending at this particular index, right? Now let's solve it row by row. So we will first be going to the initial row and we will be finding the histogram state. So our histogram initially will be equals to 1 1 0 1, because we have just seen one row. Okay, so these are indices 0 1 2 3, and now our stack here will just be having a single dummy item where the height will be -1, because all the heights will be mentioned as positive. If you see here, the values are 0 or 1, right? So the height cannot go to negative. That is why the dummy height is negative, because I will never be finding a height less than 0, and the index is -1 as well, which is out of bound, and the previous count, that means the count of valid submatrices, is 0 at this point. So why I have entered this is inserted so that you will never hit the case of stack being empty. Otherwise, if you don't include this, then you have to do a special check for the stack being empty, right? So that will increase the runtime complexity somewhat. But let's now proceed with the solution. Now in this case, we will be going cell by cell. So if you go on the histogram, you will be checking the top of the stack. So this height is 1, the top of the stack is -1. So this is increasing order, and that is why you have already found the previous smaller element. It is at index -1. This current index is 0. So what is the gap? 0 minus -1 is 1. 1, and then you multiply this 1 by height. Height is 1. So what is the total count? The count is equals to 1. Okay, the previous count is 0. So if you add the previous count as well, then the total count is going to be only 1. Right? So the current count is 1 here. So you can insert the current count, which is 1, which happened at index 0, and you will say that the height is 1. So this value will be inserted, and you will have a total counter. The total counter will be initialized with 0, and as soon as you see that, okay, one count has to be added, one count will be added. Now you move forward to this one. Now at this one, whenever you see that you are not seeing the smaller item, you will just pop it off. Okay, now you see that -1 is smaller than this one. Okay, what is the gap? 1 minus -1, that means 2. 2 is the gap, 1 is the height, so 2 times 1 is 2. Plus, what is the previous count? It is 0. Okay, so the count here ending at this index 1 is going to be only 2, which is 1 and 2, right? So 2 count will be added to the total count, and this total count is going to be 3. Now what we will insert? We will insert that the height is 1 currently at index 1, and the current counter is 2. Okay, that has been inserted. Now you go to the next cell, which is this cell. Okay, so these two cells are done. We are at 0, 2. That means at histogram at 2. At this point you are seeing a 0. So you will be popping this out, because this is a larger value. 1 is larger. When you see -1, then you know that it is the smaller element. What is the gap here? 2 minus -1, which is 3. And 3 times, what is the height? 0 is 0 only. So the count will be 0. What is the previous count? It is 0. So total count is 0. 0 will be added to 3. It will remain the same. Now what will be inserted? You will insert height 0, which happened at index 2, and the previous count is 0 as well. Previous count is 0. You move on to the next cell. At 0, 3 you have 1. You see that this 0 is smaller than 1. Okay, fine. What is the gap? 3 minus 2, which is 1. What is the height? 1. 1 time 1 is 1. Plus, what is the previous count? It is 0. So this is going to be 1, and that is why the total counter will be incremented by 1. And what we will be inserting? We will insert whatever is the height and the index 3 and the previous counter 1. That's it. And we are done with this row. We are done with this row, then we will be restarting the same process for the next row. And when we go to the next row, we have to reinitialize the stack. So let's reinitialize the stack with the value -1 -1 0. So this is the dummy entry. And let's start the process for this one. Okay, so what will be the histogram update? The histogram will be the previous histogram. You add the values. So 1 will be first added. This will become 2. When you see a 0, then you know that you have to write a 0, because on top of 0 you cannot have 1, because you cannot have any count of submatrix ending at this 2, 1. That's why it has to be 0. If you see a 1, just add the value. If you see a 1, just add the value. So you have 2, 0, 1, 2. Okay, now you process on this. So when you go to this 2, this -1 is smaller. So indices are 0, 1, 2, 3. So what is the gap? 0 minus -1, which is 1. And what is the height? 2. So 2 times 1 is 2. What is the previous count? It is 0. So the current count is 2. 2 will be added to the total count. It becomes 6. And what will be inserted? The current height, which is 2, the index, which is 0, and the current counter, which is 2. And we will go to the next cell, which is the 0. Now since it is 0, you know that nothing will get inserted, because this will be popped out and then you will stop here. What is the gap? It is 1 minus -1, which is 2, and the height is 0. So this is going to be 0. The previous count is 0 as well. So the current counter is 0. Okay, so it will remain to be 6, and what will be inserted? The current height, the current index, and the current counter. That's it. We will move to this one. When you go to this one, you know 0 is smaller, so you will stop. What is the gap? 2 minus 1, which is 1. What is the height? 1. So 1 into 1 is 1. Plus, what is the previous counter? It is 0. So this is going to be 1. Okay, so 1 will be added to the total counter. It is 7. And now what will you insert? You will be inserting the current height, which is 1, the current index 2, and the current counter 1. And we will move forward. When you look at this 2, this 1 is smaller. So you will stop. What is the gap? 3 minus 2, which is 1. So 1 times 2 is 2. Plus, what is the previous counter? 1. So the total count of submatrices ending at this point will be 3. 1, 2, 3. Right? 3 is the count. So 3 will be added and your total counter is 10. And what will be inserted? The current height, which is 2, the current index 3, and the current counter 3. That's it. We are done. Once you are done, then again we will be going to the next row and we will have to update the histogram. So let's update it. So we have all ones here. You can just add up the values 3, 1, 2, 3. That's it. And let's reinitialize the stack. So we have reinitialized the stack with values -1, -1, 0. Now let's process for 0, 1, 2, 3. When you start at this point, then you know that -1 is smaller. So what is the gap? 0 minus -1, which is 1. So 1 times 3 is 3. Plus the previous count is 0, which is 3. Okay, so 3 is added and this becomes 13. And what will be inserted? The height, index, and the counter. Fine, you move forward to 1. When you are at 1, 3 is larger, so you pop it off. Then you have -1. Okay, -1 is smaller. So what is the gap? 1 minus -1, which is 2. 2 times 1 is 2. Plus, what is the previous counter? 0. So 2 count of submatrices end at this point, 1 and 2. That's it. So 2 will be added and this becomes 15. And we will be inserting height 1, index 1, count 2. Move forward to 2. Now at this 2, 1 is smaller. So what is the gap? 2 minus 1, which is 1. 1 times 2 will be 2. Okay. And the previous counter is 2, which will be 4. Right? So we have to insert here. First let's update the total counter. Let's make it 19. And we can insert the height 2, index 2, and the counter 4. And move forward to this 3. Now you see that 2 is smaller. Yes. What is the gap? 3 minus 2, which is 1. 1 time height 3 is 3 plus the previous counter is 4, which makes it 7. So add 7 to this 19, which makes it 26. Okay. And now we need to append this value in the stack. So this will be height 3, index 3 and the previous counter 7. And we will move forward, and there is no other index left and there is no other row left as well. So whatever is the total counter at the end will give you the count of total valid submatrices ending at each of the cell. Okay. So this is the entire approach using the previous smaller element monotonic stack with the largest area in histogram solution. I hope you were able to understand this. If you see this entire solution, we have gone through each of the cell exactly one time, and there are mn number of cells. Now since this is a monotonic stack, an element can only be inserted one time and removed one time, and then it can never be inserted back again. So the total operations for each element is only 2 times, one push and one pop. So that is why we will consider it of the same order. We will consider it constant. And so the total time complexity is going to be order of mn. And we have not taken any extra space other than the stack, which gets renewed in each row. So the size of this is order of n. Okay, so the space complexity is order of n due to the monotonic stack, and the time complexity will be mn. So this is the optimal solution. I hope it is clear. Let's now look at the code. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we are given the matrices. I have found the rows and columns and initialize the counter, which is the total counter, to 0, and the current counter, which will be counting the number of valid submatrices ending at any index I comma j as the bottom right corner. Okay. Now we will be taking the histogram of n size, which is the number of columns, and initialized with all the 0 values by default. Now we will be iterating for each of the rows. Now for each row, the first job is to update the histogram height, and that is what is done here. Now after updating the histogram, we will be taking a stack and pushing a dummy value with the height, index and previous count as -1, -1, 0, so that we never run into a case of stack being empty. And then we will be running for each of the element in this particular row number I. So whenever we see an element, we will be trying to find the previous smaller element using the concept of monotonic stack, and as soon as we do that, then we will be calculating the count of valid submatrices ending at this index I comma j, which will be equals to whatever is the height here, height multiplied by the gap that we already know, and the gap is j minus stack dot top. And to this we have to add the previous counter, because you already know that if I have a count here ending at b as the bottom right corner as let's say 10, and a count here at a, that means the count of valid submatrices ending at a as let's say 6, then the count of submatrices ending at b will be 16, because all those submatrices ending at a can be made to extend and end at b. Okay, that's the reason we are adding this value. And once we are done with this, we need to push it into the stack as the new state, as I had shown you in the dry run, and increment the total counter with the current count. So finally we will be returning the total count of submatrices ending at each of the cell I comma j, which contains only ones. So I hope this entire solution is clear. If you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.